you have a provider template and a consumer template, and they are able to already communicate with each other.
I already get
All right,
it.
okay. Then, yeah, that's probably the entry point for you.
I will find everything there.
Absolutely, yes.
Thank
If
you.
you don't find anything, you can text me this other QR code.
Yeah, I also already have you in contact. Thank you very, very much. Thank you for your presentation.
Thank you.
You are awesome. Thank you.
Awesome, awesome.
Oh, that's-
We have time for one more question. Anyone want to have a question with Antonio? Anything want to ask? All right, then let's get a round of applause for Antonio. Thank you so much.
Thank you.
Amazing presentation, man. Are you guys excited for the next session? It's going to be for Gavin, Wu, and Pierre. But we're going to come back in a little bit. The session going to start at 2:20. All right, but they're going to broadcast here, so you can be here. Look for your seat. We come back in about less than 6-7 minutes, and we're going to start. All right, I'll see you guys in a bit.
Welcome everyone. And for those in the room, welcome to Startup Space A. Next up, we have Pierre Albert from Parity Technologies. Please welcome Pierre to the stage.
Thank you and welcome everyone. I see the room is packed, and I know it's not for Gav. I don't think I need to introduce Gav to you. So I don't know exactly what you want to talk about, but I am pretty sure it's about Jam. And because I got a Jam presentation quite a few times, I will tell you how I see Jam, what I think we could do with this thing when it will be built. So from a user perspective, not like the details. Gav will explain to you how it works inside. But another perspective is how we can use it. So for me, Jam is kind of a low-level layer, like even in the infrastructure. You can think about it like an operating system, something which is like really, really low, and most people will never care about it because they will never see it. And this operating system or like distributed computer will run things like parachain or contract, and that should be transparent both for the parachain and the people running contract. Like it's just the engine below which is changing, and you should see nothing. But the interesting thing about Jam are like, okay, so maybe there are plenty of interesting stuff. So what I like is it's simpler than the current relation system. So what I hope is the Jam system will be like easier to reason about because there will be less feature inside, and the set of feature is much more like reasonable, and people will build on top of that. So the simplicity is a super important thing. It will reduce complexity, allow people to reason about it, and build better system later. The second thing I like about Jam is it's a very generic system. So you could imagine to build things that are just not possible right now. And one I really like is this idea of running a long-term program. It's not like a smart contract that runs for like 6 seconds and like need to finish like in a block time. You can imagine to have things running there that run forever. So in terms of programming model, it's much, much closer to things that we are used to. You build a main program, and the program is running on-chain, like over time. And it can do things across blocks. It can just run, and you pay with contact. And the idea is to have a programming model which is close to Erlang, if you know it. So Erlang is an old language that has been used a lot by the telco like kind of world, and it's a message passing stuff. So in Erlang, like you have actors, and they just exchange messages with each other. And that's one of the things that Jam is designed to build. So the way I think about Jam, like when it will be built, and we have done all the migration on top of it, is you will have like the classical parachain model, the contract model, and I'm sure people will build new things. Possible, like this actor model, like if you think about it, it's a very classical way to write a program, and I think a lot of people will be attracted by that, by the fact it's like a model they know. Like I'm new to the Web3 world, but like smart contract and parachain, that's very, very specific things. Writing a program which has a main and can exchange messages like between threads or whatever, like that's something everybody knows. So that opened, I think, quite a lot of like opportunity for people that don't know the blockchain world, and they can write stuff in a way which is more similar to what they know. And I think this is an attractive property. With all of that, you can get an idea how you can use this thing. What you don't have yet is when. So the when part of like this is like unknown at the moment, and we will have more confidence in a few months to give you an idea, for example, when a prototype you can play with will be available. Like if we are lucky, it's at the end of the year. There are still many unknowns around Jam and the chain, like the new relation on top and how it should work. But that's progressing like quickly. So let's say that things are converging and we will have a first version that you can use, I hope, at the end of the year. After that, there are other properties, but they are less useful, at least right now. So one is like composability. Like Jam is doing some nice like co-scheduling of things on the same machine, which allow you to have like things like that talk to each other and which they are close by. And Jam also allows you how can I explain that? So maybe this part I'm not so comfortable, so I will not talk about it and not tell too many stupid things. So when can we benefit from it? I think it's a bit too early to tell how that will be a production stuff, like when. What I would like you to encourage you to do is to think about how you can use it. Like soon, like the new RFC will be published, so people can have a good idea of what the interface looks like. And you can start to think what you would do with this thing. And I think 24, 25, there are the years to make experimentation and understand how we can leverage the new technology. And then later on, it will be a production platform, like well supported and whatever. For me, it's an exciting new stuff. Like I like this idea to be able to like have radical new ideas popping up and like to have a path and a flow to integrate that into the current stack. So there is like many challenges in front of us, but like they are like reasonable challenges. So things will happen like over time. When we will have more confidence about the API and the timeline, I think that will be the right time to communicate to you all, like to tell like it's not a research project anymore. It's something that is like soon to be useful. Is a big man here? Not yet? So it's not that I don't want to continue to talk, but I don't have like super interesting things to say about that. This, or at least on Jam. Do people know when Gav will be here? Not yet. Okay. More complicated now. So what could go wrong? So that's a question I have very often. So like a lot of research projects, like there is a lot of expectation because there is a new thing coming and everybody wants to use it. But like on the other side, for example, one of the questions we have very often at Parity is, do we wait for Jam and implement the new feature on Jam, or is Jam like too far away and should we implement the feature in the current Polkadot 1 stuff? And it all depends on the timing. If Jam is a solid thing in 12 months, I don't want to spend heavy engineering time to do things on Polkadot 1. But if for some reason it's 3 years to get some things, then of course it would make sense to implement the feature in Polkadot 1. So that's a stressful like, kind of thing because we don't know yet. So the Gav team will have in April, so now it's soon, a first prototype, and they think that will give them confidence in the timeline. Because the timeline is more like, is it 1 year or 2 years? It's both exciting because it's new, but it's risky because like we are taking a lot of risk betting on something which is new, and we are telling people, you included, that we want to migrate everything on top of it. So I don't know how to manage expectations. Like I want you to understand there is a fair amount of risk in the roadmap right now, and that is not something that is coming like tomorrow. And on the other side, as soon as they start to have prototypes, I would like you to start to think about how to use the prototype. So with that, I think Gav is around, and I will let him present Jam like in much more like technical details and much more precision than what I can do. Please upload. and I will talk to you soon. Bye.
Hello. Thanks, Pierre. Right. Is that working? No? No? Yes. Okay, good. Right, so today's talk is an update on what we've been working on in what might be termed the sort of research and development arm of Parity. And the sort of code name for the project is Jam. You probably know this, or well, you possibly know this from an RFC that I opened 6 months ago called Core Jam. And what I want to do is just give you, make it clear exactly what Jam is and what it does and why we're doing it. Hands up if you already know something about this. Do you maybe read the RFC, or you've seen another talk, or whatever, right? Okay, like 5 people. So good. For most of you, this will be new. That's sort of good. There are elements of this that I'm telling you about because, it's fun and it's interesting, even if it doesn't actually directly affect what you're doing. And there are other elements that actually do directly affect what you are doing, probably. And so I'll point these ones out with sort of a big asterisk, so you know to be like listening. But the other bits you can kind of just like go ooh and ah if you like. All right, Jam. It stands for Join, Accumulate, Machine. It actually comes, as I mentioned before, it comes from Core Jam, collect, refine, join, accumulate. That's the computation model that the machine implements. It's shortened to Jam for a couple of reasons. One of them is that the actual chain itself only does the join accumulate bit. The collect and refine stuff happens off-chain, so it kind of works in that regard. It's also a little bit shorter and therefore faster to type. And it works quite well with the machine thing at the end, which is what it is at the end of the day. It's a possible direction for Polkadot. I'm hesitant to say it's the direction. That's not really for me to say exactly, but I'll come to how I see this sort of rolling out at the end of the talk. So for now, we'll just say it's a candidate design for what would follow on from the relay chain. Now, if you were here yesterday, you'll know that I sort of said I expect this to be a sort of a singular upgrade rather than a iterative thing that we've been doing at the moment. There's a few reasons behind this. One of them is that there is only certain things that you can do with a sort of big bang upgrade that you can't do with an iterative approach. Like, for example, restrict precisely what can be done after the upgrade. I'll get onto that a little bit later. Another reason, and I think maybe a more salient one for this audience, is to try and avoid this constant drip of minor upgrade after minor upgrade, breaking change after breaking change every week or two or a month. This is obviously going to be a bit of a breaking change. Hopefully, we'll try and minimize that to the, a very manageable bit of a breaking change. But better to have one breaking change than 5 marginally smaller breaking changes at various times throughout a year or two. It's a new concept of a blockchain. It takes quite a lot of concepts that have been floating around, but it brings them all together, and I think it does it in a way that hasn't really been done before. We might call it a domain-specific chain, sort of maybe a more general thing for an app chain, like the domain-specific chain, a chain that handles one particular domain problems. In this case, roll-ups, what Ethereum folk might call optimistic roll-ups, but roll-ups that are heavily bounded in terms of their security, something that most of these things are not. And in reality, this is what Polkadot has been doing for the last, I don't know, whatever, 4 years, 5 years. It is a roll-up chain. It's just disguised as a parachain hosted chain. But in reality, the relay is already a highly domain-specific roll-up chain. It's just got a little bit more opinionation than we want. And that's essentially what Jam here fixes. Now, there's a bunch of other things, but what I'm going to do is, rather than talk about them in this one big, slide, I'm going to split them out into lots of smaller slides so we can talk a little bit more about each one. Okay, so the Jam concept. Right, it's a domain-specific chain, okay? So it does one particular thing. It's not a general purpose chain. In many respects, when you see the Jam chain sort of specified, you can see there's quite a lot of similarity to a smart contract chain. In particular, the Jam chain allows code to be hosts permissionless code actually on the chain itself. Very similar to what a smart contract chain does. It's not a smart contract chain, though, for a number of reasons. But it's quite nice that it has some of these properties, and it allows us to make direct comparisons for some things. Okay, why is it not a smart contract? Well, actually, I'm gonna wait until the next slide to dive into that. Specifically, what the Jam chain does is it accepts outputs of rollups, right? Of bits of computation that have been done already. So these bits of computation are done elsewhere, and then whatever data they yield is fed into the Jam chain. The Jam chain's job is to essentially provide the necessary apparatus to ensure that this output correctly reflects the input when it goes through whatever transformation it's meant to have gone through. Okay. Again, this is like fairly basic stuff for what rollups are. And furthermore, and probably most importantly, or more, at least as importantly, the Jam chain is there to integrate the outputs of these computations into some shared state. Right, so it provides this model, this shared state model for integrating outputs together. This is relatively, we can see how, if you compare what Polkadot is doing now, the relay chain, we can see how it fits into this model. But interestingly, we can see how other chains, like what Ethereum is doing, also fit into this model. It's a very general model. In the Jam chain, we arrange the state of the Jam chain into different encapsulations, encapsulated components. A little bit like smart contracts. This is one of the similarities that the Jam chain has to a sort of smart contract chain. We call these encapsulations of state services. We don't call them contracts. There is a good reason for this. Creating a new service is permissionless. Anyone can do it. So this is a little bit like you can create a smart contract on a smart contract chain, right? It's unlike what you can do in general on a substrate chain, where you need to be whatever the chain's governance is to be able to add a new pallet, right? So you can add a new service into the Jam chain without asking anybody for permission, without going through any governance mechanism. Services are, they can be defined, they're defined in sort of a tuple. If we're looking for like a formal definition, it's quite similar again to a smart contract. There's a bit of code there. There's a balance associated with the service as well, and there's some state associated with the service. That's actually again fairly similar to what you'd expect on a smart contract chain. It's key value pair sort of thing. There's a couple of other bits associated as well that I'll go into. Code itself is split into 3 different bits, 3 different entry points. It's the same code blob, but it's got 3 different sort of ways of getting in there. And this is really the crux of what of Jam's model, what the service offering of Jam, what Jam actually wants to do. So the three sort of bits of code, the 3 entry points, it's 1 bit of code, sorry. 3 entry points into this bit of code are refine, accumulate, and on transfer. Okay? So refine is the bit that does the mostly stateless computation, right? This is the bit that defines the transformation for the rollup for this specific service, right? Accumulate is the thing that takes the output of that and folds it in to the overall state of the service. And then on transfer, as you might imagine, handles things coming from other services. Yep. Okay. So we've got like an idea now. Our state is partitioned into services. You can add new services into the state. The services have code attached to them. So far, so good. Very similar to how a smart contract thing works. What we haven't talked about is how the input to a service actually gets brought in. Well, we've talked about it a little bit, this refine and accumulate. I'm going to do too much. Work packages are effectively the input to a service. In fact, they're not specifically work packages, but a work item. Work packages can have many work items in them. Okay? You know, work package can have a few work items. Every work item is associated with a service, and it reflects the actual input to the service. This is where, if you're doing something like, I don't know, a parachain service, this is where you would put in the transactions, right? All that stuff to do with you know, blockchain inputs. The refine entry point defines how we go from a work item, like an input, to a work result, which is basically the output of refine, right? And it's the thing that eventually gets fed into accumulate. So we have this 2-stage processing. First refine, then accumulate. So work items are refined into work results, and therefore a work package, which contains many work items, is effectively refined into a work report, which is the results of the corresponding results of several items. Okay. A work package can be assigned. It uses 1 core for 1 time slot, always. 1 core on the jam machine, for 1 time slot, 1 6-second period of time. Now, how does it differ from a smart contract chain? Well, it's transactionless. This is actually how Jam differs from, as far as I know, every other blockchain. There are no transactions in Jam. Everything that is all permissionless input first goes through a refine stage. So the service pre-refines all of the input, and then the input, that input is transformed into these work reports, these sets of work results. And then those work results make their way actually onto the chain. So there's no transactions, very important. So if there are no transactions, how does anything make its way from the external world in? Well, there's still extrinsic information, but these are not arbitrary, they're not of an arbitrary format. they are of a specific format. In most cases, there can only be one thing that the block author can put in its place. Now, there are 5 kinds of extrinsic in Jam: guarantees, assurances, judgments, pre-images, and tickets. Okay? I won't go too deeply into what each of these things mean at this stage. Guarantees and assurances are essentially the validators each getting together or putting forward their attestations that a work result, that help ensure a work result is indeed the correct result of its work item when transformed through the service's refine function. This is part of the security apparatus of the Jam chain, essentially. Judgments, again, are part of the security apparatus of the Jam chain, but they get used in exceptional circumstances. Essentially, when a work result has made it all the way through and sort of, even though it's kind of broken, even though it's not reflective of the work items that it purports to be, has already been made its way through the system and has been since accumulated into its services state. At this point, we have to roll things back and we have to record the fact that this was invalid. Now, the way that we judgments generally come, in fact, I think it's a necessity that judgments come within 1 hour after, or at most 1 hour after the work report has been submitted to the chain. So basically, you've got this like 1 hour period where things could be not quite reverted, because finality will, in this case, pause until the judgment has been allowed to actually happen. In general, though, this is like a massively upper bound, and most 99.999% of the time, any possible judgment would have been done within maybe 3 or 4 blocks after the work package, and finality would only be paused for that long. Okay, so those first 3 things actually represent the security apparatus. Pre-images are a service, a piece of functionality that the Jam chain provides specifically for the refine function. So I mentioned the refine function is essentially stateless. It is essentially stateless, but there's one particular thing that it can do that is kind of stateful, and that is it's allowed to look up the pre-image of a hash. So if it knows that there's a hash, and it knows that the hash, or it believes that the hash has been has its pre-image registered on the Jam chain, then it's allowed to ask for it, even though it's not necessarily known that the whoever it is that's actually executing this work package is synced to the Jam chain. I mean, this is a relative thing. Different nodes can be synced at different amounts. But there is logic actually on the Jam chain that ensures that this is secure. And for those pre-images to actually get onto the Jam chain, there has to be some way, right? And that's what this type of extrinsic is for. This is actually, of all of the things, this is the one that is opinionated. A block author of the Jam chain may choose to bring in one pre-image rather than another pre-image. There's nothing that like holds them to any particular pre-image. Whereas for those guarantees, assurances, judgments, and tickets, there are particular pieces of information, pieces of data, which the author either has or doesn't have, and if they have it, regardless of whether they have it or not, their only option is to either provide it or not provide it. There are no, they can't like provide something else in its place. Tickets are essentially anonymous entries into the block production mechanism. They do not immediately need to be provided to produce a block, but rather we run 2 epochs in front. This is part of an algorithm called Sub0, which is a small refinement of an original algorithm called Sassafras, which you may already have heard of. It's slowly being integrated into the Substrate SDK. I won't go too much into that. It's not so relevant for this specific talk. Now, one of the things that Jam aims to bring is a reduction in the opinionation. Polkadot's quite heavily designed around one particular service profile, right? The delivery of parachains. This is what the original Polkadot paper had in it. It's like, parachains. Polkadot is a service for parachains. In delivering that service, Polkadot created a number of very useful subcomponents, one of which was the distributed data availability system, another one which was the essentially an optimistic roll-up system with very good and proven security guarantees. And it's essentially, Jam could be considered essentially a reduction in the level of opinionation. Basically, a greater level of abstraction and generalization so that it's easier to use these underlying components in a way that you would like to use them. And there are some use cases which it's very hard to use them for. And this is alleviated with Jam, and I'll go into that in a little while. All right. So, as I mentioned before, Jam is permissionless. So Jam hosts code very similar to a smart contract chain in this regard. People can upload code, they can expect Jam to execute that code. It also hosts data, this lookup, this pre-image lookup that I just talked about, and state, essentially very similar to a key value pair, key value store. Anyone can introduce new services. In fact, the first service that would be in the Jam Genesis block would be a service that enables people to add new services, right? Since Jam itself doesn't have any way of transacting, of accepting transactions, there's no immediate way for anyone to create a service on Jam. So there has to be a service that starts in Jam to allow people to, go through it and create their own services. So that first service will indeed do that. Services are not limited. They don't have any particular limits on how much code, data, or state they can host. It's all cryptoeconomic based, so the more, essentially the more dot your services the more dot your services have deposited with them, the more data, the more state they can have in them. One example service, just to put something in your mind. What is a service? Well, it's a pretty abstract thing. What is a smart contract? It's a pretty abstract thing. Well, what is a service? An example service would be the parachains service, right? Not a specific parachain service, but the parachains service. Essentially, all of the Polkadot 1.1 functionality would be contained within a single service on Jam, right?
Core time Jam.
But the kind of cool thing is that other services can be added that provide other functionality, but still use essentially Polkadot's distributed availability system and essentially auditing and guarantees system for computation. All right, let's have a deeper look into the service model. So when you make a service, this is the model that you have to express what you want to do under. I mentioned before, it's a two-stage thing, refine, accumulate. In fact, there's this third entry point on transfer. Refine accepts potentially up to a lot of data, 5 megabytes of data, okay? It's a really substantial amount of data. This is roundabout. This 5 meg figure is, potentially it could change by the time of launch, of deployment. But it might be that if we can manage 6 megs of data, that would be quite nice, because it would be every time slot, and a time slot is 6 seconds. So it would be a very nice round 1 megabyte of data per second. Refine yields up to 4 kilobytes of data, right? So you've got this like big sort of compaction factor going on. Why? Well, because this is the nature of the distributed availability system, right? It's distributed. You can't have all of this data making its way into this single sort of crucible that is the accumulate function, that is the on-chain logic. So it's important that you know, we compact somehow. We provide an expression of this 5 megabytes of data, whatever that means, in terms of the changes to the overall state of the system. It's important that we express that in this 4 kilobytes. So to give an example, for a parachain, the 5 megabytes of data would be something like the proof of validity block, right? It's basically this bunch of information that includes the block header, the transactions, and any witness data that the block is going to draw upon from the parachain state. The 4 kilobytes of data would be something like the state root after all of that has been integrated into the parachain state, as well as maybe the message queue heads, so you know what messages have been sent from the parachain, and maybe some header data, some header information for the most recent header of the parachain. Essentially, it's the stuff, if you're familiar with the internals of Polkadot 1, it's the stuff that will go into the candidate receipt. The refine function can execute for up to 6 seconds of PVM gas. Now I'm going to go into what the PVM is in another slide. Essentially, it can execute for the full block period, right? At the moment, PVFs can execute, I think the limit is 2 seconds, so it's about a third of the period. This can be, because PVM has basically secure metering, and because there's a few other optimizations that we're doing, we can actually extend that, so we can process 3 times as much stuff. The refine function also gets some contextual information on what it is, on the world around it, that the work that it's doing is being produced in. In particular, it gets information on what other things are being refined at the same time. Why is this important? Well, it means that you can construct work packages that have multiple services, work items of multiple services in them, which are codependent. And this then enables certain things like, for example, accords, and the ability to have one service, like, I don't know, make that like some sort of EVM service, interact synchronously with a parachain. Inside of Refine, you can also make pre-image lookups. So this is the thing that I mentioned before. If you have a hash and you believe that the pre-image is available for that hash on the jam chain, actually on the chain, then you can request the pre-image by giving it the hash. What this allows us to do is, for example, look up code. So we might have, for example, a parachain code where you don't want to supply a parachain code, which could be, I don't know, upwards of a megabyte. You don't want to supply that inside of the work package. That would be a waste of the 5 megs, right? Every time you want to run the parachain supplying the same 1 megabyte. So instead, you store the 1 megabyte of code on the jam chain, and you just have its hash in the work package. You say, yeah, I would like this, the pre-image to this hash. This, for what it's worth, is what we already do on Polkadot 1, but we do it in a slightly suboptimal way, and very much not general. Now, that's refine. That's the first stage. That's the bit that does all the work. That's the workhorse, but it's largely stateless. Then we've got accumulate. What accumulate's job is to do is to integrate the output of this workhorse of refine actually into the world state, into this global shared singleton, right? Into the blockchain. Now, Accumulate accepts multiple outputs from Refine, all of the same service, right? Don't forget, Refine and Accumulate are both entry points from a code blob that is specific to a service. It accepts multiple Refine outputs, basically a big vec or a slice, whatever, right? And it processes them. And it can do what it wants as it processes them. And it can execute for a much smaller period of time, per output around, at most, 10 milliseconds. And this depends whether the work package it has many different work items in, or if it's just one. If it's just one, it gets the full 10 milliseconds per work output. If it's many, then that's shared between each of the outputs of the work package. Crucially, and in big difference to Refine, it's stateful. This means it can access the state of the jam chain. It can read the storage from any service, and it can write to its own key value store. It can also transfer funds and send a little memo when it does transfer funds. And it can also create new services, obviously, upgrade its code, request the availability of a pre-image, and a few other bits that I'm not talking about. Incidentally, and I actually forgot to mention this in the Refine model, both of these can invoke child instances of the PVM. Yeah? So you can make a new instance of the PVM that's sort of sub-instance, a virtual machine, and you can put some code in there and put some data in there, set the memory to whatever you want, set the stack even to whatever you want, and then kick it off and let it run for some period of gas, and then it will come back when it's done. So it's a very, very flexible model for computation. Onwards to on-transfer. So on-transfer is also stateful. You can alter alter the service's state. It can't do any of the higher level stuff like, transferring funds again and upgrading code and so forth. That's specifically for Accumulate. But it can look at other services' state and alter its own state. And this really is there so that you can allow for services to communicate with other services in a, albeit asynchronous fashion. So it's a little different from many smart contract platforms in that this interaction of the encapsulated components, smart contracts or services in our case, this interaction happens in an asynchronous fashion. You fire off a message along with maybe some tokens, and then on the other side, at some point later, actually later in the same 6-second execution period, but still at some point later, the other service will get it and can execute upon it. There's no return path. If you want a return path, you have to do a transfer back, basically, or possibly change your state in some way that the sending service is going to can expect it and look at it later. Both Accumulate and on-transfer are written so that they can be executed in parallel. So the different services, accumulates and transfers, can all execute at the same time. This allows for, it's not really exploited at the current design, but it would allow for future designs to actually have more than this 10 milliseconds of gas. In principle, there could, for example, be a secondary core, CPU core, utilized for executing certain accumulates and giving them much greater amounts of gas to use. All right, so let's move on. PVM based, Poker VM, or it's sort of actually, it's morphed a little bit. So for those of you who read the forums, you may already have heard of the Poker VM. It's a parity guy, Jan, has implemented a RISC-V transpiler, basically, with some modifications that make it go really very, very fast indeed. The spec of the machine, so the sort of design, the ISA, if you like, is de facto PVM. The actual implementation, Jan's implementation, will stay with Poker VM. So it's PVM based. So the design of the protocol, PVM-based. Not to say no one else, obviously other implementations of PVM are not only possible, but encouraged. The PVM design is based on the RISC-V ISA. Don't know if you're aware of this, RISC-V. It's like, it's been around for almost 10 years now. It's a very simple instruction format. I think at its basic, at its core, I think it's only, 20 or 30 odd instructions, and they're mostly very simple things like, and, or, add. PVM adds a few extra instructions. The nice thing about the RISC-V ISA, other than that it's very easy to transpile into common hardware formats like x86, x64, and ARM, is that it's well supported by tooling. So LLVM, I think it actually just recently got merged. The RISC-V output platform, whatever, is actually part of the LLVM official targets now. Now PVM itself is very simple. It should be possible to actually implement a compliant PVM, admittedly interpreter, in a matter of a few days, rather than something like WebAssembly, which would take probably quite a lot longer. It's secure, by which we mean it's sandboxable. It's got various guarantees over execution, and it's metered, or at least it's friendly towards being metered. And of course, deterministic, consensus sensitive, capable of being used in the sorts of applications that we need. It can host arbitrary code. What do I mean by arbitrary code, and why is it different to WASM? It's a pretty basic machine, right? If you've studied computer science and you've sort of been introduced to the sort of, a very, very simple machine, it's not far off that. It doesn't have much of the complexity that you might otherwise find, nor does it have much of the opinionation that you might otherwise find, or optimizations for certain use cases. WASM is ultimately optimized for a web use case, and this is sort of fine in most circumstances, but one way that it's not so fine is how it handles the stack. The stack is not handled as part of the machine itself, but rather it's sort of off machine. And this creates certain issues when you want to use it for things like continuations. Now, continuations can be really very helpful thing to have, particularly when you're doing stuff like asynchronous programming, and that's probably something that some of you have come across if you've tried to do any XCM. RISC-V being such a simple and sort of regular machine, just puts the stack in a bit of memory, which means if you snapshot the whole of memory, or at least the pages that are actually used in memory, you will end up being able to have continuations just by the by. It will happen naturally. There's nothing extra to do. And this is something that we very much intend to make use of in some of the use cases for Jam. Now, as it happens, PVM also achieves incredibly fast execution speeds when run on regular hardware. And as I say regular hardware, I mean basically x64, but also potentially ARM instruction set, something like the M1 or whatever. How fast is blazingly fast? I asked Jan for some updated benchmarks. He hasn't got back to me yet. But as of the most recent benchmarks, about the same speed as WebAssembly when it's the fastest WebAssembly transpiler when it's not metered. When WebAssembly transpiler is not metered. So we can do metering for free, basically. And we get all of this extra helpful stuff thrown in as well. The continuations in particular make this a potential game changer for when we want to write code that is meant to go, that is meant to scale across something multi-core, something highly parallelizable like Jam. And to be honest, this is how, realistically, this is how all blockchains are ultimately going to scale, right? This idea of just like throwing faster and faster single core CPUs at it is not going to go very far, right? We already can see this in hardware. And if you've been in software for the last 20 or 30 years, you'll have seen this in the evolution of software platforms as well. Increasingly, there's a great need to think in terms of asynchronous, parallelized architectures, and the same will for sure be true in blockchain. So it's consensus algorithm, specifically the block production algorithm is Sub0 based. Now Sub0 itself, as I said before, it's basically a simplification of Sassafras. It throws out some of the less important bits that may still possibly be useful for parachains. So it's not necessarily that parachains are going to use Sub0. They may probably stick with Sassafras, but really, for Jam, one of our main considerations was to make this thing as simple as possible. Why? Partly because we want to ensure that it's as minimally opinionated as possible to maximize the potential like future use cases. Another reason was to follow in the footsteps of Ethereum 1, yellow paper, and really try to get as many implementations of this thing as possible to try and like kind of spread the expertise. Because at the moment, Polkadot is a very complicated little beast. It works, but good luck if you want to try and understand end to end exactly how it works. Well, with Jam, my sort of personal goal is to make this something that someone who is capable of reading and understanding the yellow paper would be able to read and understand within at least a week or so. So simplicity is crucial. So as I said, Sub0 is a little bit more simple than Sassafras. For those who don't know, it's a snark-based consensus algorithm, a snark-based block production algorithm specifically. It uses snark specifically for their anonymity features, and it delivers constant time block production, almost entirely fork-free. There's a couple of instances where they're outside instances. They basically only happen when there's a net split or someone's being intentionally malicious. But there are a couple of instances where forks could possibly arise, but in all likelihood, unless there is something really crazy happening, Sub0 will be fork-free. And the sort of great value for the anonymity is not specifically to keep validators' identities sort of a secret. In fact, when they actually produce a block, they give away their identity anyway, but rather for ensuring that the block production mechanism itself is secure, basically to avoid spamming. Validators can't be DOSed. Very crucial point, perhaps not so obvious. It's capable of offering the same service as Polkadot 1, right? As what is happening at the relay chain at the moment. Jam can host Polkadot 1 style parachains. That's designed with this in mind. The main sort of elements that would change on the substrate side, substrate and Polkadot SDK would still be used, but the PVF itself would be retargeted. So instead of targeting WebAssembly, it'd be targeted towards PVM. And we actually expect PVM, because it's such a minor alteration from RISC-V, and RISC-V is now an official LLVM target, we expect PVM to be an official LLVM target before this stuff is deployed. Now, it doesn't just host parachains. It does other stuff that Polkadot can't do. Well, the relay chain, I should say, can't do. It brings key features to parachains. In particular, it brings the possibility for removing most of your benchmark work and alleviating that in the future. It brings the possibility of having this multi-instance, multi-sharded smart contracts to police and enforce certain rules of interaction between parachains, accords. And it would necessitate, I don't want to say deliver, but necessitate full XCMP, which basically means lifting that limit on on how much information can be passed via, passed between parachains, usually using XCM. Now, Jam is built with Agile core time in mind. Not much changes on the Agile core time front. I presume people here are familiar with Agile core time. Yeah, nodding of heads, good. So, this whole, NFT sales market thing for core time, that would remain essentially unchanged. The main thing that Jam adds to Agile core time is the ability to not simply target core time at a parachain, but to target at, well, essentially arbitrary sets of work packages. Yep. It has an entire layer that I don't have time to talk about, unfortunately, today. That will have to be the subject of a future talk. It has an entire layer that handles authorization. I say an entire layer. It's like 3 equations, but it's like it has an entire a small section of design specifically on this authorization system that enables very agile authorizations to go along with the Agile core time. Now, Jam's design is the hard bits. The great thing about sort of doing Jam is that the hard bits they're already done, right? The hard bits are things like distributed availability and managing the security for the computation, secure computation of PVM, of this input to output, these roll-ups, basically. And that lets us concentrate on doing, the more easier, not always so easy, but some of the easier things. And certainly the things where if you get them a little bit wrong, it's not going to be, super bad for the whole thing, for the whole system. Unlike, for example, if you get availability a little bit wrong and things just stop working totally. So one of the things that we've sort of been focusing on is optimizing networking. We've optimized a few things. Networking for Jam uses the Quick protocol. This allows us with very large numbers of validator. I mean, very large, not large like Ethereum, but still 1,000 plus validators. We can have direct connections between all of them. So when I say M to M, I just mean many to many. So essentially all 1,000 plus validators can have a persistent connection to each other without, potential issues with sockets and so forth. We avoid gossip, as much as we possibly can. There are some instances where, in very, very niche edge circumstances, there may still be some like random selection message passing stuff. But basically gossip is avoided, mostly because we don't need it, because we don't handle transactions. We handle, right? Transactions are removed from the protocol. We just handle these very fixed function extrinsics. And with the fixed function extrinsics, you kind of already know exactly who they're going to go to, and you know whether to keep them or not. So we don't really need this sort of optimistic gossip thing. Where we do need to distribute something that's not point-to-point, or within a very small subset, we use grid diffusal which I think may already actually be implemented in Substrate, but in any case, this is not merely something that is additionally implemented. This is our primary mechanism for sending out information across the whole validator set. Grid diffusal, for those, if you can't already guess, basically we arrange the validators into a grid, and we send the package, by a row, and then each item on the row, each node on the row sends it to all members of its column. This provides, a pretty optimal way of getting data across the entire network quickly. Yeah. One of the other ways that we've optimized is pipelining. Now, this is something that I'm a little surprised hasn't been done before. The header of blocks in state-based blockchains since Ethereum generally contains the posterior state root, right? Basically, it's a digest of what the state has become after doing all of the various computation that the block implies. Yeah. Now, this means that you can't send a header out, so you can't, when you're making a block, you can't send the header out until you've done all of the computation that implies. Now, there's some bits of computation you probably do want to do before you send it out, because they may imply, or a failure, or the result of that computation may imply that the block is not valid. But for any of the stuff that you need to do that can't fail, to the degree that that sits at the end of the block, that you don't need to do anything after it that can fail, well, you can send the block out in principle beforehand if you are not required to know what that posterior state is. So with Jam, we don't put the posterior state root in. Instead, we put the prior state root in. So the state roots that are featured in the header run one block behind instead of one block in front. And because of this, it means that we can do all of the cheap stuff, like probably about 5% of the block's weight, or the time to actually execute the block. We can do that computation and then send the block out immediately after that point, distribute it to the other validators, and then carry on doing the infallible stuff, 95% of the block's computation, effectively just the accumulation, ready so that we can check the next header that we get, prior state root. This means we can effectively start constructing the next block before we've finished executing the last block. So we can both publish one block, receive, start computing, and start building the next block, all before actually having executed all of the implied computation of the current block. This means we don't need to be quite so pushed for the computation that we do in this 6 seconds. So, for example, if we have 6 seconds between blocks, which Polkadot does at the moment, but it has to provide the posterior state root, then we can't use all 6 seconds for the computation, right? Because we have to do the computation, work out the posterior state root, finish up the block, send it off, have other people, the next block producer in particular, be able to import it, which means recomputing all of that implied computation, verifying the posterior state root, and then constructing the new block. So basically, we have at most half of that 6 seconds to actually do the computation. But by pipelining, we get up to the whole 6 seconds. Now, of course, you don't really want to use all 6 seconds to do your computation because, well, no one would ever be able to catch up normally to the head. They'd be constantly running behind. New blocks would be produced at approximately the same rate they could import old blocks. But what we can do is get much closer and probably get 3.5 seconds worth of block computation time rather than, say, 1.5 or 2 that we have at the moment. Now, one of the architectural differences with Jam over the relay chain is that the Jam chain fixes quite a lot of the functionality, quite a lot of the pipeline. The relay chain does fix some things. I don't know if anyone can guess what. So it fixes the language, the meta language really, by which the protocol is defined. It fixes WASM. Yeah? You can only upgrade a relay chain to another WASM blob. You can't upgrade it to like a PVM RISC-V blob or whatever. It fixes a couple of other things, or at least makes them very difficult to change. For example, the type of the type used for encoding the block header or the hashing scheme. So there are some things that that Polkadot does effectively fix, but Jam nonetheless fixes more things. It doesn't fix everything. In particular, much of the flexibility that we get from the WebAssembly meta protocol that we've used it for with Polkadot relay chain would still be similarly flexible with Jam due to its service model, right? Effectively, the service model takes over the upgradability responsibility, and the chain itself is not designed to be upgradable. Why not? Well, for 3 reasons. Firstly, simplicity. It's a lot simpler to not do that. Secondly, there has been a sort of a tendency towards introducing complex functionality and not removing old complex functionality from the relay chain because it can be upgraded so easily. Essentially, it just follows whatever the current state of the substrate SDK is. And there's no great need to simplify the substrate SDK. You know, we have Rust compilers and trait systems and stuff that kind of manages that complexity. But what it means is that essentially no one is going to be able to re-implement Polkadot, and that's unfortunate. The third thing is that it provides huge potential for optimization because we know what the various things that the Jam chain has to do are, and we know we can fix the parameters. We can optimize for those specific parameters. Things like network topology, timing can all be optimized, whereas they wouldn't be able to be optimized so easily when we have essentially the ability to alter everything with every upgrade. However, the application level functionality, things like core time sales, staking, governance, this can all be done, all be upgraded because it all sits inside of a service. Even stuff like the parachains logic, so the ability for parachains to service message queues and all this sort of stuff can be upgraded within the service. So Jam does one kind of application level thing. It's not really application level because there's no user interaction and no direct user interaction. But what Jam does is it will associate a token balance with a service. So services hold tokens. They can not any token, the specific token of the Jam chain, but while they're agnostic to things like governance and staking, they're not agnostic to the token. The token is a first-class piece of functionality. What this means is there's an opportunity for it to be used. The economics of this token, because it's impossible to, well, it's not impossible. There's always hard forking, but it's not so easy to upgrade the Jam chain it becomes possible to credibly fix certain economic elements of this token. It's not possible on a purely upgradable chain such as the Polkadot Relay chain, because, well, you can arbitrarily, if you want to, just double the issuance and hand it to whoever you want. If you can control the outcome of a particular vote in governance, you can do that. Nothing can stop you doing that. Essentially, economics is subservient to governance. Now, this may be a sensible thing, it may be a reasonable policy, but the point is that the relay chain cannot disallow this as a policy. It's de facto the policy. It's the only policy that it supports. The Jam chain supports the possibility of having a policy whereby governance is not able to control the economics. And this is an interesting opportunity. Now, one of the things, I mentioned it yesterday, for those who were there, one of the things that we're doing with Jam to try to ensure that Jam is, sort of lives up to its initial expectations is to create a test rig for the Jam chain. And it's not one of these, little mini test nets running on questionable hardware that, keeps the cloud compute costs to a sensible level. This is a sort of fairly hefty investment. So there will be a Jam, call it toaster. So basically a test rig for full-scale trials and measurements of Jam. This is one of the things that held us back with development of the Polkadot Relay chain, was the inability to actually work out what the emergent effects are, what the dynamics were of having a network at that scale. Right? The best we could really do was have a few dozen nodes on a test net, and then Kusama. But Kusama isn't great for monitoring, because of course you can't look inside everybody's validator node, and a few nodes on a test net, which does give you this in-depth ability to investigate, isn't so useful because, well, you can't really simulate what it's like to have 1,000 nodes. This Jam toaster will be able to give us this level of research. We'll be able to create a network that is the full scale of Jam, which is to say 1,023 nodes, and it will allow us to investigate how the network actually runs at that level, and basically provide to you guys what precise performance characteristics you can expect for your parachains. So let's talk, I'm a bit over time, but I've only got 10 more minutes, so I'm just going to push through. I want to talk a little bit about Jam and Substrate, how Substrate and Jam are going to interact. This is the asterisk bit, right? This is the bit where it's like actually relevant, so you can sort of prick your ears and listen. All right, so the first thing, mentioned it in passing, benchmarks are optional. What do I mean by optional? Well, it's not that that no one will ever need to do benchmarks again, but the most of the time that you need to do benchmarks, that need will be averted with the Jam chain. Why? Because Jam is fundamentally a metered system, which means you can check to see how much work you've done after you've done it. You can also game theoretically sort of limit how much computation is done. I say sort of game theoretically because it's not something that you would do inside of the parachain itself. You would rather do it at block construction time, and you would just throw out a block that used more gas than it was meant to use. For what it's worth, I use gas when I talk about metered time, and weight when I talk about benchmarked time. There may be instances where you still want to do benchmarking, essentially where the metering, which isn't necessarily going to be quite conservative for the PVM, like, we have to meter for worst case to make it secure. when that metering is a little too conservative for your use case and you want to eke out an extra 20 or 30% performance, say, maybe, whatever those numbers are. Hopefully it'll only be 5 or 10%. Then there's also the possibility that you might want to benchmark something when it can execute for a really long time, and you want to make sure, and it's up to the user parameters that will determine how long it executes for, and you want to make sure that it doesn't execute, it's not going to execute for that long. Yeah? All right, next thing, XCMP. So Jam, as I mentioned before, it requires full XCMP. Why? Well, because we kind of fudge things a bit in the relay chain. We allow more data to be passed in via a candidate receipt than would make sense if all parachain passed in all of that data all of the time. Jam has, being more general purpose, is more rules abiding. Right? It has rules that it expects all services to follow, even the parachain service. And part of those rules are this, as I mentioned early on, this limit as to how much information can be passed from refine into accumulate. And that effectively dictates how much the upward message queue can pass. Essentially, how big those messages can be that go through the relay chain. At the moment with HRMP, all of the messages go through the relay chain, and therefore all of the messages a parachain would have to send would have to fit into this 4 kilobytes or whatever. Probably not that realistic. And therefore, XCMP, where in fact you only pass the message heads and the actual message data is sent off-chain, would be the obvious and much needed fix. Accords. So I've talked about Spree a little bit, I've talked about accords a little bit. So if you're not familiar, accords are these sort of encapsulations of state and logic, smart contracts if you like, that have multiple instances, sit on each instance sitting next to a parachain, and they sort of send messages between themselves and allow for a parachain to do some synchronous interactions with them. They could be used for all sorts of things where there is no good trust relationship between parachains. For example, tokens. You might want to guarantee that a parachain will honor its side of the teleport when you receive a teleportation signal. At the moment, you need this reserve thing, right, where you have a reserve and you send a message to the reserve, and then the reserve sends a message onwards to the actual destination. And it's a bit annoying for a few reasons. One of them is, of course, it's slower and more costly to have this extra chain involved. But a very important reason is that there's no trust relationship, or the trust relationship between the destination and the eventual and the source is broken by going through this third party. Yeah. This means if you've been doing XCM coding, you'll have noticed a clear origin being inserted into some of your messages when you're using reserves. This is to reflect that lack of trust that the source and destination have between each other when the message goes via a third party. Well, with accords, that wouldn't be needed, basically because they could teleport tokens directly between themselves. They wouldn't need the third-party reserve. But also, another accord could be an XCM forwarding accord that guarantees that even if a message comes via a third party, it is the same message that was sent originally by some source. And this means that you could essentially get rid of that clear origin, that annoying clear origin. The last thing I want to mention before we get onto the conclusion is one of the things I think is I get asked about occasionally. Jam, because it provides a much more general, less opinionated model for using these underlying cores, right? This underlying consensus, secure, resilient resource that the validators provide. It makes doing certain more exotic things like the usage of distributed availability for things like zero-knowledge proofs, it makes it much more sensible and efficient. In particular, Jam enables this mixed resource consumption model. So a work package can utilize or can contain both work items that are, say, very heavy in terms of computation, but not so heavy in terms of the amount of data that they need to be made available, and other work items that come from services that are the opposite way around, right? That have lots and lots of data that they want to make available, but don't need to do much computation at all. So while the validators themselves are still have a very standardized sort of homogeneous requirements for things like bandwidth and computation, the services and the work that the services want to do in Refine can be very different. And by mixing and matching and putting together services that use a lot of one resource and not so much of another with their opposite counterparts, you can make much better use of the job that validators are doing. In essence, bringing down the cost, right? One of the more obvious ones is, utilizing distributed availability and maybe a little bit of snark verification, stuff that requires relatively little computation, but a lot of the availability, and pairing that with, say, a parachain workload, which would use a lot of computation, but not necessarily so much of the availability. You drive down the costs for both. I've mentioned XCMP. I don't think I need to go into that again. So let's talk a little bit about how I see this unfolding. And obviously this is something that I've jotted down. I haven't thought too deeply about it, and I'm not. This is, after all, a fairly decentralized, quite chaotic process. So I don't want to. I don't want this brought up and used against me in 6 months. But I hope that it won't be too far off the mark. So we've already seen the preliminary RFCs, Sassafras, precursor to Safrol, and Core Jam, precursor to Jam. These are the two sort of key technologies that are in there, along with PVM. These have already they're already sort of up. So the next sort of steps would be a draft of the proposal, which is coming soon. Some initial implementations. Notice I say the plural there. We would, once those are in place, open an RFC for discussing this and presumably making some changes. There are already question marks over points of the design that I can't get into. I'm already way over on this talk. So, but needless to say, there are design elements that are not certain, and I think a period of RFC of discussion to work out where they should land is probably a fairly sensible thing to do. Following some months of that, I cautiously estimate between 3 and 12, probably centering on about 6, but let's see. There would be the final draft of the proposal, which is basically a draft specification, and an RFC that says, this is what we want Polkadot to turn into. There'd be then ratification, which would basically be an on-chain vote from fellowship and governance, or one or the other, I don't know, something along those lines, probably both. And then I guess that would take, I don't know, maybe a month or so, and then implementations. And again, the idea is with Jam to keep it simple, but there would also need to be substrate tooling, and not on here would also be things like the development of the key services, in particular, the Polkadot 1 parachains service. Substrate tooling there would also include things like XCMP. Now, I'm guessing this would bring the timeline to like 6 to 18 months, depending on precisely how much the ratification and discussion process took. I am assuming that the substrate tooling and other bits of development, service development, would be happening essentially in parallel with this discussion period in the months before. Finally, in very optimistic 8 months, probably fairly cautious 20 months, I see that being the sort of timeline for deployment and actually getting the relay chain transitioned if all of the other steps get completed successfully. Okay, I hope that has given you some idea of my thoughts for the future of Jam, and I don't know if there's any time left for questions. Maybe not. Is there? One? Okay, whoever wants to ask one question, I will take. Cheers.
Jam is the successor of the Polkadot relay chain.
Mm-hmm.
Is there a successor of the Kusama relay chain?
So, I mean, I see Kusama as being, it's the canary network of Polkadot, right? So it should really do this transition before.
Okay.
But, that depends on the governance of Kusama. So that would be the proposal. And, Kusama governance could vote to say, no, this is where it ends. Kusama is its own thing. It's going to stick with this relay chain architecture. To be fair, Polkadot could do the same. It could say, no, we don't want this. We want to stick with the relay chain architecture or go some other direction. But I don't see many other suggestions for where the relay chain should evolve into. So, and it seems to me this is a pretty good. This makes sense to me anyway. So I would vote for this. And yeah, I don't know. If Kusama goes that way, then we'll see this rolled out onto Kusama in the months before Polkadot.
Would you see both chains running on, would it be the same set of cores? Is that possible on the core jam layer, or would they have separate sets?
Separate sets.
Okay.
Yeah.
Thank you.
All right, cool. Thanks a lot, guys.
Thank you so much, Gav. So just before you all leave me to go on a quick break, please let me do a quick plug-in. So Polkadot Decoded tickets are now available. The next event will be in Brussels, Belgium on July 11th and 12th. Please be the first to purchase early bird tickets. There are only a limited number. And on March 14th, so in 2 days, they will be on sale to the general public. So take your discounted tickets now, scan the QR code, and then we'll see you at 4 p.m. in this space. See you later. Thank you.